function theta from AB to, oh, okay, it's not very good to write it this way because they have different r from AB to r plus, and the function theta from AB to r, and these functions are continuous, so that gamma of t has the following coordinates: r of t cosine theta of t, r of t sine theta of t. We did it a couple of times, and this is there is nothing new in that. So there is a choice of the radius function and the angle function on the curve, only on the curve. So as you can easily see, r of t is simply the distance from gamma of t to the origin, or maybe to p. No. Plus gamma of 0. That is the right. Gamma of 0, just a moment.
No, plus
P. Just a moment, yes, plus p, not gamma of 0. I somehow decided that it starts at p. And theta of t is defined uniquely up to adding a multiple of 2kp. Okay, but I want to do it to present this result in a bit different manner. So here I have the interval a, b. Here I have r2. Okay, let the point P be here. R2 without P. And gamma is a mapping from here to here. The image of is a curve. Now let me do the following. This is the r-axis and this is the theta axis. This pair of functions define a mapping from the interval to this right half plane. I will call this mapping tilde. It takes in t and produces a pair r of t, theta of t. Since r of t is positive, that's what it does. Okay? So, if I consider all t's, I will get a path in this right half plane, and this path is called gamma tilde, and is called a lifting of gamma. And it is obvious that I can map it from here to here. This lifting is mapped into this curve. Take a point, lift it, and send it to the point which is obtained from here. So this is an important notion. The path can be lifted to a mapping, to this mapping, a mapping from a path in the right half plane to here. And okay, as you see, this is uniquely defined. Theta of t is defined up to 2k pi. What does it mean? That lifted path can be raised or lowered by a multiple of 2 pi. Okay? And the most important part is the following. If gamma t is simply gamma restricted to the interval at, t between a and b. So if I take a part of my path, okay, then theta of t is nothing else but theta of a plus 2 pi change of angle gamma t p. That is an important formula that I want to. It is obvious. This is simply the change of angle divided by 2 pi. So if I multiply by 2 pi, this will be, okay, theta of t minus theta of a divided by 2 pi is exactly by definition this guy. Okay. Now an important application of this problem. Number pi, which means 3.14, on page 41. That is the point. And this is already some important. Let gamma delta be paths which have same endpoints. Two paths. The following assertions are equivalent. The following assertions are equivalent. First assertion, gamma is homotopic to delta in R2 minus pi. So these two curves can be connected by homotopy. Here. Secondly, gamma p equals delta p. They have the same W invariant. Change of angle divided by 2 pi. And 3, if gamma tilde, delta tilde are liftings with the same initial angle, initial point, then gamma and delta have the same final point. All three of these are equivalent, and this is quite important. We know some implications of this. For example, if two curves are homotopic, then these numbers are the same. We know this. We proved this a couple of times. But, and this is true not only for this domain, it is true for any open domain. But in this particular domain, the converse is also true. Why do we need this? It is important in the process of proving. Let me prove this assertion. 1 implies 2 is known, even not only for the plane without one point. It is known for any open domain. We did it already with the help of this rectangle and switching to small subrectangles. Okay. 2, 3 is obvious. How? From this formula. You see? What happens to different liftings? The liftings, there are several liftings possible, but what is the difference between them? They can be shifted up and down by 2 pi, that's it, by multiple of 2 pi. So, if I take two curves, and they start at the same path, okay, and they start, okay, they start at the same point, then I can put B here, the other part. Then the angle at the end is going to be the same. Because it starts, theta of A are the same, that means they start at the same point. Okay? And since these guys are the same, T is B, the whole. Then we get the same. So far so good. But now I need to prove number 1 from here. Then I will be done. Then I will see that all of them are the same. Okay, let me try to prove number 1. So imagine that I have, let me draw a picture, 2 liftings, they have the same initial point, and 3 implies that they have the same final point. And they all live in the right half plane. Okay? The right half plane, it has very simple topology. It is as if they live in a huge rectangle. You remember this? And any 2 curves with the same endpoints in the rectangle are homotopic to each other. Any 2 points are homotopic. They're homotopic to, these 2 curves are homotopic, they're homotopic to each other. How can I do this? For example, I take gamma of t, this point, and delta of t, connect them, and this connection is, this connecting segment is going to be within this rectangle, correct? And I can do homotopy. Gamma of ts is 1 minus s gamma of t plus s delta of t. Check that this is a valid homotopy. And if s is 0, you get the left path. If s is, actually I need to put this. And it is, if s is 1, I get delta tilde. So they are homotopic. But what did we use here? We used the fact that the right half plane is a convex domain, and in the convex domain, any 2 curves are with the same ends are homotopic. We did it. So 3 implies that gamma is homotopic to delta, and 3 says that they have the same ends and they're homotopic as curves with the same ends. Okay, and from now on, okay, it's not a big deal. From this, one follows. Why? Because if I can make homotopy here, I simply map it here, correct? And I will get homotopy here. So these curves can be mapped here, exactly as we did before. Yes?
I'm confused about something simple. If gamma tilde and delta tilde have the same initial point, why aren't they the same curve?
No, they're not. They're not the same curve. They have the same initial point, but I know that W of, first of all, their radii may be absolutely different. I say nothing about their radii.
So what does it mean for gamma
Okay, that's a very good point. Gamma tilde, this means, okay, for each gamma you have functions r and theta. And for each t, you can make a point with coordinates r of t and theta of t. These points are r of t, theta of t. And t changes from A to B. Therefore, you get a curve. And this curve is called a lifting. So, I know only that this is equal to this for gamma equal t equal b. Correct? For the whole curve. So what I know is that the final angle of gamma tilde is the same as the final angle of delta. The final angle of gamma is the same as final angle of delta. Okay, it's very good. I just need to explain.
Gamma tilde and delta tilde, just to confirm, they're liftings of the same path gamma?
No, no, no. They're lifting of two paths. Of gamma and tilde. Gamma and delta. I have two paths here. I have two mappings from here to here. And they're lifted to different paths here.
I see, there are two paths, I see, between the same 2 points.
Yes.
I see, okay,
The important thing is this condition makes sure that if you start at the same point, which you always may assume, because the initial points are the same points here, and you can choose the initial angles to be the same. But if you choose the initial angles to be the same, then the final angles have to be the same because of this condition. So what we did, we switched from a path here, and it has a bad topology, isn't it? We switched to paths on the right half plane, and right half plane has very good topology.
This is an example of a universal cover.
Yes, sure, the question is about the universal cover. Yes, definitely. I simply, he talks about universal cover, but since I do not see any immediate pluses of discussing it, I discuss to push it forward. Maybe I will have to return to it at some time, at some point. Okay, is everything else clear?
This is something that's so trivial, it's hard. And sort of the hard thing is to figure out what the rules are. Everything you're saying is so obvious.
It is not awfully obvious. There is a non-obvious thing there which says that if you have two curves in the right half plane with the same beginning and same end, and the fact that the ends are the same is due to this fact, okay, then they are homotopic, and this is the homotopy. Then you have to do one small thing more. You must understand that this homotopy produces a homotopy here. And this homotopy is not going to touch this point, simply because the radii are strictly positive here. The radii are strictly positive.
Okay, so then you need the other mapping from gamma, from that plane, the half plane, into R2.
And there is a mapping. It is called the, this mapping, well, to some extent there is such a mapping. I better put it this way. I consider gamma of Ts for any fixed S. Okay? If I fix S, then I have T changing. And this has coordinates R, some R, T, S, cosine theta, Ts, R of Ts, sine theta of Ts. Does it? This is a curve here. S is fixed. then simply fix S, and then you get a curve. Where do you get this curve? In the plane which does not touch the origin. Which does not touch the origin. Okay? And this is, and definitely for different S's you have, at one is S0, you have gamma. If S equals 1, you have delta, and definitely it is continuous, because everything is continuous here. Okay, but let us now talk about it. Okay, just one moment more, and I will talk about this. Because this is an important point. Let me do one problem more. And this is the next problem. Problem 315, the same page, 41. It is almost the same problem, but gamma delta are mappings from AB to R2 minus P, continuous, closed. Closed meaning gamma of A equals gamma of B, and delta of A equals delta of B.
I'm still stuck with the problem.
Okay, very good.
Yeah, so I really don't see that we've shown that 3 implies 1.
3 implies 1.
So
3, okay,
I guess why I'm confused is
they are liftings with the same beginning points and end points. So we've got two curves in the right half plane with the same beginning and the same end. But because the right half plane is convex, then these two curves are homotopic. So gamma is homotopic to delta. From this it follows that gamma is homotopic to delta without, and that's what I was explaining, and I can explain it.
the reason I'm confused is I can draw two curves in R2 without P, point P, that are not homotopic.
No,
No?
yeah, sure you can draw, but they are not going to come from two curves with the same endpoints. Definitely you can draw it. You got it? They are going to have different endpoints. Very good. Now actually it seems to be the same problem, but now two curves are not having the same endpoints, but rather they are both closed. And then the following: gamma is homotopic to delta as closed paths. There is a different kind of homotopy. You remember this? If and only if W gamma P equals W delta P. Well, how do I prove it? I prove it along the same lines. So the fact that this implies this is trivial. We already know this. Homotopic closed curves have the same winding numbers. Homotopic closed curves have the same winding numbers. You remember this, right? Again, how did we do that? With the help of this rectangle, dividing into subrectangles and so on. So this is trivial. trivial, not trivial, but proven already. Secondly, I want to prove that the equality implies that I take gamma delta. Okay. Now I cannot say that they have the same initial point, because they live in very different places. But what I can say is the following. Okay. This is, let this be, an important thing is that the end radius is the same as the beginning radius. And the difference between these two is 2k pi. It is 2 pi times this, correct? Unfortunately, delta lives in some very different place. And again, it is something like this. Okay. How do I do this? Just a moment, please. Let me do it this way. First of all, I can shift one of the curves so that, for example, I have two curves. It is gamma and this is delta. And this is p. I can shift both curves so that they have a common point. I can shift it here and I can shift it. At least one common point. Can I do this? Sure I can, because when I shift a curve, its winding number doesn't change. You remember this? Okay. So, when I have done this, then I can easily assume that the initial point coincides. Okay? This is the initial point. Then the end point will coincide also because of this condition. Is it clear or not? So the first thing is that these two guys live in absolutely different places. Okay? But have the same winding number. So what I do, I simply move them. They are living outside of. That is a small problem. Okay, I need to be very accurate about this. It's just give me one moment, because I'm thinking about a different way of doing this, and I was pretty sure that I had that way. Oh, okay, I do not need all this move. Yes. Sorry, move is being cancelled, because you see, P can be inside, easily can be inside, and then when you move, you better not touch this P. Huh?
You can still form it. So
Yes, I can deform them, but let me not do that. I have a better idea. So, lifting them, I get two curves in the right half plane. And what do I know about these curves? The end point and the beginning point of each of these curves have the same r coordinate. Correct? And the theta coordinates can differ by how much? By 2 pi this. And there is another curve. The initial and the end points are on the same vertical line. And these angles are differing by the same amount. Okay? Now what I do is the following. Connect these, connect this. And consider gamma tilde of Ts to be 1 minus S gamma of T plus S delta of T. What do I get? The important thing is that for every gamma Ts and this gamma, what is S is 0, gamma T 1, they are going to be on the same vertical line, because gamma of T, because gamma of 1 and delta of 1 are, gamma of 1 and delta of 1 are on the same vertical line. Gamma of 1 and gamma of 0, okay, I'm sorry, I make things much more difficult than they are, simply because I am very lazy and do not draw pictures. Do not write formulas. So, consider this. Let me check that gamma of 1s minus gamma of 0s belongs to the vertical line, is parallel to the theta axis. That's what I want to prove. That's what I want to prove. So these two guys are on the vertical, but this is easy because this is 1 minus S gamma of T of 1 plus S delta of 1 minus 1 minus S gamma of 0 plus S minus S, I'm sorry, and delta of 0, which is 1 minus S gamma of 1 minus gamma of 0 plus S delta of 1 minus delta of 0, which is, these are the same vectors, call them A, that's what a gamma of 1 minus gamma 1 minus gamma of 0, delta 1 minus delta of 0, they're the same vectors. So I get, add them up, I get A. Correct? And this vector is parallel and whatever. So what I get is, I get a family of curves. And this family gives me the first curve when S is 0 and the second curve when S is 1. And then I, as before, I simply consider the related curves in the plane without the point. Because of this condition, this equals A. These, the related curves, will be all closed there, they close out, correct? And we have a continuous family. Done. Done? You see, I know that I can be very convincing, but it is different from being, from providing a proof. In this case, I would like to provide a proof and not being convincing. When I wave my hands very convincingly, it sometimes makes a substitute for a proof. Okay, is this clear? Nobody objects? Convincing, okay, that's good. Okay, but this is, let me just dance around this a bit more. and try to explain what does it mean. It means that the class of homotopic closed curves in the plane without one point is completely determined by the winding number. So I take gamma and send it to this number, gamma in R2 minus P. Okay? What does it say? It says that equivalent gammas go to the same numbers, correct? And moreover, this mapping is reversible. So it is called this pi 1 R2 minus P is Z. Pi 1 is called the fundamental group. The fundamental group of the plane without a point is Z. And this is the mapping. Homotopic group, I don't want to discuss its group structure, but the homotopic space, if you wish, is the set of equivalence classes of closed curves. The set of equivalence classes of closed curves. And this mapping, the winding number mapping, it assigns an integer number to every class of homotopically equivalent closed curves. What do I know? First of all, that this mapping is 1 to 1, and this is this fact. And it is easy to see that this mapping is mapping onto, because consider this is P, consider this curve repeated 25 times in this direction, and you will get the winding number 25. Consider this curve winding 25 times in the opposite direction, and you get the winding number of minus 25. So actually, this is a one-to-one mapping of the fundamental set. I don't say anything about groups yet. Fundamental set of the plane without a point onto Z. But Z is obviously a group, so there should be a natural group structure here, and there is a natural group structure here, but I don't want to discuss it right now. And then this is a group isomorphism. This is a group isomorphism. Let us try to think a little bit. Imagine that I remove not one point from the plane, but 2 points. What is the fundamental group of this set? Z times Z, Z squared. Because what you need to know the winding numbers around each of these points. If you know these winding numbers, one can prove, it is a proof still, that everything is going to be okay. This is a mapping one-to-one onto. And knowledge of the fundamental group is very important in a lot of equations of topology, differential equations, physics, not what, just you mentioned what not. But here is the first time we have computed the fundamental group of something non-trivial. What is the fundamental group of the whole plane? Trivial, 0. Because any two closed curves on the plane or on a square, whatever, are homotopic to each other. So there is only one element, one class of equivalence, one element in the group. But if you, for example, try to think about spheres, what is, if you consider one-dimensional sphere, that is a circle, what is its homotopy class? Z, because you have this guy, you can have, say, you go half circle there and back, and definitely this can be contracted to a point. So this is a 0 element. But if you go once, you will get something else. If you go twice, you get something else, and so on. It is easy to see that the fundamental group of a sphere is Z. Of one-dimensional sphere, I'm sorry. What is the fundamental group of two-dimensional sphere? It is trivial, because if you have a closed curve on the sphere, you can throw away one point from the sphere, and then this sphere becomes the plane, and then you understand that you can contract it to a point. What about four-dimensional sphere? Also trivial, for the same reason, because the homotopy group is trivial, the fundamental group is trivial. But you might think about high homotopy group. It is just something else I want to discuss. When you consider, okay, that's an important part. What is a closed curve? You can say that it is a mapping of the interval to whatever, but so that the ends of the interval map into the same point. Instead of that, you could think not about an interval, but about a circle. And you map a circle somewhere, continuously map, and the image will be a closed curve. So the fundamental group is related to mappings of circles into whatever you want. But your next step is what? Let me map not circles, but spheres. And consider homotopy in the invariance of these images. Then what you get is, say, the second homotopy group. Then you might think about mapping not spheres, not two-dimensional spheres, but three-dimensional spheres. And you will get what? Third homotopy groups, and so on. And the calculation of homotopy groups of spheres is a very nice problem. It was solved, well, when was it solved? In the 60s, I believe. Something like this. About 60s. And it was not at all trivial, it was moreover, it was very non-trivial. But now I will tell you something quite startling, and it happened to be of great importance. Consider the sphere of a Hilbert space, infinite-dimensional Hilbert space. A huge guy, right? It is much easier, its structure is much easier than the structure of any fine-dimensional sphere. It is contractible. So all homotopy groups of the infinite-dimensional sphere are trivial. It was proved by Cooper in the early 70s. No, in the 60s, definitely in the early 60s. And then it happened to be very important in K-theory developed by Atiyah and Zinger, though I think the initial motivation for Cooper came from a very different subject. But that is something really very interesting. Infinite-dimensional sphere topologically is much simpler than any of the finite-dimensional spheres. So going to infinite dimensions sometimes makes your life much easier. It is not a big deal. It's not difficult to prove the Cooper's theorem. Not a big deal.
Are you saying okay, first of all, on a sphere of any dimension, Sn, all curves are contractible to a point?
Curves, yes. But the spheres of greater dimension are not contractible. The nth, if you have a sphere.
But the sphere is not contractible.
Yes,
Yeah.
The images of greater spheres are not necessarily contractible.
Okay. And the statement is that, I guess, pi infinity
No, no.
is trivial.
No, no, no,
Okay,
no.
then
Okay, then let me explain it better. Okay, let me put it this way. Consider the infinite dimensional sphere. There exists a one parameter family of mappings of the sphere into itself, continuous mappings, so that when the parameter of this 0, you get a identity mapping. Sphere maps to itself. And when the parameter is 1, you get another mapping. Sphere contracts to one point. It contracts by itself to a point. I can briefly explain why this is so. Okay, if you have a two-dimensional sphere and you have a one-dimensional subsphere on it, it is an equator. Can you contract the equator to a point? Staying on the sphere? Yes, you can. You simply go north, 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 and you end at the North Pole. You see? So extra dimension allows you to contract equator along the sphere to a point. But if you did not have, if you had only equator, it cannot be contracted to a point on the equator itself. But extra dimension allows you some freedom. But if you have infinitely many dimensions, then whatever sphere you have, fine dimensional sphere, you can go to extra dimension and contract it to a point. But Cooper proved a bit more. He proved that the whole infinite dimensional sphere can be contracted by itself to a point. It is a bit more difficult. Cooper, that is the way to write it. I think Nicholas Cooper of Switzerland. Yes.
I was just going to make a comment, but it's probably also worth mentioning that these homotopy groups are really important for understanding some physics. If you have a field theory, for example, and you want to understand what are the stable solitonic configuration, monopoles, domain balls, that sort of thing, that's a question about mappings of fields. Vector fields take values in some Lie algebra, and then you want to know what are the mappings of the sphere and infinity onto that Lie algebra. In general, some kind of coset space, mod H would be an H or Lie algebra. And knowing that, knowing what these homotopy groups are, tell you what the stable configurations are. So I think it's really powerful for...
Yeah, it is. Sure, but I would say, I think this kind of physics applications were developed in the last, say, 15, 20 years, no more than that. Yes. My feeling is that, say, in the 80s, I do not remember any results of this sort in the 80s.
In the 80s, I know that...
Or maybe 70s.
The study of inflation or grain unified theories and vacuum structure. Those groups.
So the thing is that these groups, the fundamental group and higher homotopy groups, are very powerful invariants of the topological spaces. And let me make one comment more. Actually, I understood it quite recently, though it is mostly due to my own stupidity. Why these things should be so useful? There is a simple reason why they should be so useful. Imagine that you have two topological spaces, and you want to study maps from one to another. You want to study continuous maps from one to another. And the space of continuous maps might be very, very complicated. But then you start thinking, okay, if I don't know how to classify maps from any topological space to any topological space, maybe I will think about a simpler problem. One of these topological spaces is something standard. So, consider k-dimensional spheres. Okay? and consider mappings of k-dimensional spheres into M1. What is this set up to homotopy? It is the homotopy group, correct? But if I have a mapping phi from here to here, then I get a mapping phi composed with phi capital from here to here, correct? That means that I get a mapping phi star from pi k of M1 to pi k of M2. So each mapping from here to here gives me, through this composition, a mapping from here to here, correct? And it is easy to see that equivalent mappings go to equivalent mappings. So any homomorphy or any continuous mapping between M1 and M2 generates mappings, I will put K here, the related mappings of the homotopy groups. And if, for example, you know that the homotopy groups are such that, for example, the mapping onto is impossible, then you immediately understand that the mapping from here onto here is impossible. You see? So you reduce the problem of studying general continuous mappings of phis to the study of mappings of, say, standard groups associated with the spaces. If you know everything about the standard groups, then you know everything about, you know quite a lot about general mappings. That's how homotopy groups are important. But there is another notion, and again, the so-called cohomotopy groups. You might study mappings from here to Sk, psi. And if you have phi here, you can compose and get this. And you get the mapping phi upper star k from pi k of M2, you start with this, to pi k of M1. What is pi k upper k of M? The homotopy class of, or say cohomotopy class of mappings from a space to a sphere. And again the same, these are standard, these are now treated as standard invariants of the topological spaces. And in terms of this invariance, you can say something about general mappings. So for me, it was for quite some time, why should we consider mappings? Why should we consider homotopy, cohomotopy group? I understood why they are useful, but actually the idea is very simple. If you want to study mappings between general spaces, you better first study mappings from standard spaces to general, or from general to standard spaces. And what is more standard than a sphere? A sphere is a topological object which should be studied in full details, and it is. I think we understand everything, more or less everything about spheres. Are there any really deep problems, unresolved problems about spheres, topological structure of spheres? Don't think so. Well, the last was resolved, say, several years ago. This is Poincaré's conjecture. What is Poincaré conjecture? If you have a closed manifold which has all the same homotopy groups as a sphere has, then it has to be a sphere. If it smells like a sphere, if it looks like a sphere, then it is a sphere. And an interesting history how this was proven. The case of dimension 1 is trivial. Dimension 2 case was resolved in the 19th century by classification of all two-dimensional surfaces. Dimension 5 and higher was resolved by Stephen Smale in the very beginning of the 60s. The higher dimension is, the more freedom you have, everything is okay. 5 and higher, all this was resolved by Stephen Smale. Dimension 4 was resolved by Michael Friedman and Simon Donaldson, but Michael Friedman mostly. Donaldson made some other contributions. In 85, I believe. 85. And the only remaining problem was dimension 3, which proved to be much harder than any of the rest dimensions. It was resolved by Perelman in 2003, I believe, or 2004. And by the way, each of these steps earned the author a Fields Prize. Smale got a Fields Prize, then Friedman got a Fields Prize, and now Perelman got a Fields Prize. A good problem, each step.
It seems unfair that Snell only got one.
And again, as a matter of fact, it was a great surprise at that time that dimension 5 and higher are very, well, relatively easy. It's not a big deal. As a matter of fact, from the modern point of view, it is almost triviality. Simply because there are too many degrees of freedom you have. Dimension 4 was very hard, really very hard, but it was nothing compared with dimension 3. Dimension 3 is extremely hard.
The statement again is,
if you have a k-dimensional manifold oriented compact manifold, if you have a k-dimensional oriented compact manifold, such that all its homotopy groups are exactly as those of the sphere, of the k-dimensional sphere, then it is a k-dimensional sphere. The only question is how could Poincaré even imagine something like that and prove to be true. Okay,
yeah,
but yes.
there are people who can make conjectures
Uh-huh.
like that.
But
Be right.
you see, the only problem is that you must be right in essentially more than 50% of your conjectures. Because I can make conjectures in every field, but I will be right in exactly 50%.
About half the time I prove something, I'm still wrong.
Okay, but so far we were able to prove this very simple fact only. A very simple topological space. And we have computed, honestly computed, the fundamental group of this. Okay? Again, this was supposed to be the first 15 minutes of my talk. So, but it took a bit longer. Okay, let me now move. You see, it was a separate piece of paper. I just wanted to very quickly go through it. Sorry for being so.
We're enjoying it.
But again, my feeling is that this is really something that this idea about lifting is indeed very important, but before that I did not have a chance to get any real application of it. And so I decided to skip it, and maybe it was the right thing to do, because now I will need it quite a lot. So now we are going to be concerned mostly with closed paths. And as I have already explained, a closed path closed gamma, it is a mapping from S1 to U. Continuous mapping from S1 to U. Okay. Now imagine that we have any mapping from S1 to U. Continuous. We can treat it as a curve, definitely, as a closed curve, correct? And then we can denote, just a moment please, what is the notation? Degree, I believe. Oh, no. So if P is not in U, then the winding number of F with respect to P is the winding number of the related gamma over P. Because F, the mapping of a circle into U, is exactly the notion of a map, of a path, and we know what the winding number of a path is. Exercise is, well, we've done this exercise. Okay. A small proposition, and again we are supposed to know it already. And consider F from S1, but actually he uses the C, circumference. He uses C for that. To U. And so that F extends to a continuous mapping of the disk to U. Imagine that I have a mapping only of a circumference, but it extends to a continuous mapping of disk. Then W of F P, P is not in U, is 0. It is easy, because if I have a circumference and it is mapped to U, but actually this mapping is extended to the whole disk, correct? Then I consider the mappings of disks of circumference of smaller radii to U. They will be mappings. And they will give me a homotopy of the first closed curve to a point. They will produce a homotopy of the closed curve to a point. And the winding number of a point is definitely 0. So we already had it. It's simply he wants at this point, and I understand why, get away from curves and speak about mappings. We had the notion of homotopy of a curve, but now we want the notion of homotopy of a mapping. But there is only, say, yes?
To make sure I understand the statement is that if you can extend the mapping of the circle
Continuously
to the region inside, the disk inside, then it implies
that the winding number of the initial mapping, which you still have to be able to extend, is 0. If you are able to extend, then you are lucky that it is 0. Okay. But actually the converse is also true for a special U. Okay? If F P, let F be a mapping of C to R2 minus A. Now the U is a very specific guy. And if the winding number of this is 0, then F extends to a continuous mapping, of D to R2 minus P. But it is already not a big surprise for us. That's easy, is it? So I want to say that this is easy. Why? That's why. So f of c is gamma, correct? I call it f of c is gamma. And the winding number of gamma with respect to p is 0, because it is exactly what this guy is. Correct? And we know that the fundamental group of this thing is Z. And the winding number gives exactly this isomorphism. Correct? So it means that gamma is homotopic to constant curve. Okay? Take this homotopy and it will be exactly what you need. It will be exactly what you need. Homotopy means it is a mapping from the circle times 0, 1. But what is circle times 0, 1? It is a disk. If the one end is just 1 point. Okay? And that's exactly what we need to do. Okay, I think I ran out of my time.